Hey there! Today we're going to dive into one of the most fundamental processes in all of chemistry. It's happening right now in the battery that's powering your device, and it's happening in the cells of your body. We are talking about redox reactions. So, let me ask you something to get us started. On the one hand, you've got the super controlled, steady power coming out of a battery, and on the other, you have the wild, chaotic, explosive energy of a lightning strike. What on earth could those two things possibly have in common? Well, the answer is actually really simple and pretty profound. It all comes down to the movement of one tiny little particle, the electron. Yeah, that's it. Whether it's a controlled trickle of power in a battery or this massive, chaotic surge in the sky, the simple act of an electron jumping from one thing to another is the engine behind it all. And that really brings us to our first big idea here. You can almost think of the electron as a kind of universal currency. It's the unit of exchange that makes so much of the chemistry in our universe actually happen.
And that's really the core of it. When you strip everything else away, the whole complex world of these reactions is just a story about giving and taking. One atom has an electron it's willing to part with, and another atom is right there ready to accept it. And this simple little trade, that's what we're going to unpack today. All right, so let's put some official names on this electron trade. Chemistry has specific terms for the giver and the taker in this whole transaction. And, getting those straight is pretty key to understanding everything else.
Okay, so the formal name for this exchange is a redox reaction. And that name itself is a pretty big clue. It's actually a mashup of two words, reduction and oxidation. And that's because these two things are two sides of the same coin. They always happen together. You just can't have a giver without a receiver.
So here's how that partnership breaks down. Oxidation is the loss of an electron. Reduction is the gain of an electron. Simple enough, right? But now look at the terms at the bottom, the agent. This can feel a little backwards at first, but think of it this way. The substance that gives away its electron, well, it causes its partner to be reduced. So we call it the reducing agent. And on the flip side, the one that takes the electron causes its partner to be oxidized, making it the oxidizing agent. See, each one makes the change happen in the other.
So we've got this natural flow of electrons. That's cool. But how do we turn that into something useful? Well, now we're going to see how chemists have figured out how to brilliantly harness this tendency for electrons to move and literally use it to generate a spark. This right here is the basic idea behind every single battery you have ever used. It's called an electrochemical cell. What it does is it takes a chemical reaction that wants to happen all on its own, a spontaneous reaction where electrons are just eager to move, and it captures that movement as electricity. So how do we build one? Well, first, we separate the two partners into their own containers, their own half cells. The oxidation, the electron loss, happens at a place called the anode. And the reduction, the electron gain, happens at the cathode. Okay, step 2. We connect them with a wire. This gives the electrons a highway to travel on. But, and this is crucial, without step 3, the whole thing would just stop. Why? Because as all those negative electrons flow to one side, it would get so negative so fast that it would actually repel any more electrons from coming over. The salt bridge is the solution. It lets other ions flow between the cells, keeping the charge balanced and letting those electrons keep on moving. And that, right there, that is the big aha moment. That controlled flow of electrons moving through the wire, from the giver to the taker, that is electricity. By physically separating the reaction, we've forced the electrons to take the long way around, and we've captured their energy as electrical power.
Okay, so that's how we get power from a reaction that wants to happen. But what about a reaction that doesn't want to happen? Is there a way to force it? Well, let's take a look at how we can actually reverse the flow.
And for that job, we need an electrolytic cell. You can think of it like trying to push a huge boulder up a hill. It's just not going to happen on its own, right? You have to put energy in to make it happen. An electrolytic cell does the same thing. It uses an external power source, like plugging something into the wall, to literally force electrons to move and drive a chemical reaction that would never happen otherwise. And this table here really sums up the difference perfectly. You've got your electrochemical cell, think a battery. It takes a reaction that happens spontaneously and produces electricity. Then you've got your electrolytic cell, think recharging a battery or electroplating metal. It consumes electricity to force a reaction that's non-spontaneous. So really, the crucial difference is the direction of the energy flow. Is the chemistry giving you energy, or are you pushing energy into the chemistry? Okay, let's bring this all home.
We've gone through the mechanics of how this works, but let's zoom back out and really talk about why this electron exchange matters so much in our actual everyday world.
And honestly, once you start looking, you see this electron trade absolutely everywhere. It is the engine inside every battery and every fuel cell. It's happening inside you at this very moment. Your metabolism is basically just a very slow, very controlled oxidation of food to release energy. It's the reason metal rusts, which is just oxidation you don't want, and it's how we do things like electroplating, using electricity to coat metals. From huge industrial processes to life itself, this simple exchange is absolutely, fundamentally at the center of it all.
And that's really what I want you to take away from this. It's just incredible to think that this tiny, subatomic event, an electron hopping from one atom to another, is responsible for so much, from powering our world to the very spark that makes us alive.
So I'll leave you with this thought. We have managed to understand and harness this tiny, fundamental exchange to build our entire technological world. So the question is, what other fundamental exchanges are out there in the universe just waiting for us to figure them out? What's going to be the next electron?